All right, we're going to pick up where we left off in section 10.5, and we're developing the idea of what area looks like, or at least how we could calculate it in a polar coordinate system. And if you remember, we likened our idea in rectangular coordinates, where we had, went through too many of these slides, where we had rectangles and approximating by dropping these rectangles down to the x-axis. And instead, we're going to take a look at these sectors of a circle because polar coordinates is measuring in terms of radian lengths away from the origin and angle measures away from the positive x-axis. So this is where we were when we left off. We were talking about defining our function r equals f of theta. The rays go from theta equals alpha to theta equals beta. F is continuous and positive on the interval alpha to beta. And we'll pick up right there. All right, so then in the same way, we partitioned area under a curve into rectangles we can partition this area into sectors. Okay, so that's just what we had just said. The width of each subinterval is then delta theta, which would be theta sub I minus theta sub I minus 1, which is beta minus alpha divided by n, where n is our number of subintervals. On each subinterval, we approximate the area with the circular arc r equals f of theta sub I then the area a sub I enclosed by the curve on this subinterval is approximately the same as the area of the circular sector of radius f of theta sub I. And central angle delta theta. So a sub I is equal to 1/2 r squared delta theta, which is 1/2 f of theta sub I squared times delta theta. The total area, A, is approximately the sum, A equals the summation from I equal 1 to n of A sub I, which is the summation from I equal 1 to n of 1/2 f of theta sub I squared delta theta. As long as, sorry, that was supposed to be a capital for as long as. Let's try that again. There we go. As long as we have done this numerous times, we can improve the approximation by making n larger. Taking the limit as n goes to infinity, we have area equals the limit as n goes to infinity of the summation from I equal 1 to n of 1/2 f of theta sub I squared delta theta. But here's the kicker. This is equal to the integral from alpha to beta of 1/2 f of theta sub I squared d theta. So all of that finally puts us at the development of this theorem. And that what we just did was actually more or less the proof of this theorem as we were developing it. The area in polar coordinates. It says the following: if f is continuous and non-negative, on alpha to beta, that interval, right? And 0 is less than beta minus alpha is less than or equal to 2 pi, then the area of the region bounded by r equals f of theta, theta equals alpha, theta equals beta, so those are my boundaries, is, and this is the formula we did before, area equals 1/2 the integral from alpha to beta of f of theta squared d theta. Or, if you prefer, you can say the area equals 1/2 the integral from alpha to beta of r squared d theta. all that work to get to that formula, right? So this is why we don't often develop these in the class session, because it just takes so long to do that. All right, so let's take a look at an example. Definitely we need an example after all of that development. So here's our example that we're going to look at first. We're going to find the area of the indicated region. And I know I'm not with you to actually do this in person, but have your calculator ready and I'll still try and walk you through those steps. And hopefully we can still make use of our calculator even though we're apart to do this. So the first one, example number 1, we're going to do 1 leaf, and you'll see what I mean, why I say that, of r equals cosine of 3 theta. So go ahead and grab your calculator, and I will as well. And I want you to put this equation into your calculator. We're going to talk about what we need is we need to know what theta needs to be to make this work. So we're going to take a look at what theta is when we've looked at it generally before, which most of our thetas so far have been looking at like a 0 to 2 pi for theta. And we're going to see that happen, and we're going to see what happens on that. So this is r equals cosine of 3 theta. So you can type in cosine of 3 theta. And just for the beginning part, just go ahead and go ahead with, 0 to 2 pi. On your t-step, maybe like at a 0.1 or something like that. X min and max, this is a cosine graph. So cosine graphs oscillate between -1 and 1. So we really don't need big x min max, y min max values. So even if you went -2 to 2, it would be sufficient. So -2 to 2 would be fine. So we're going to graph this and see what happens. Okay, so you should have ended up with a graph that looks something like this. Okay, not perfect, but you have basically this idea. So it's wanting us to find the area of one of these 3 petals. And when we're looking at these, they need to be non-overlapping in order to make use of this area formula. That's why we're going to find one of these petals, not just all of them, and just sort of divide by 3. Right, so we could find, say, this petal, or it doesn't have to be that one, right? It could be this one at the top. They should all look the same. Of course, my graph's not great, but we just need one of these 3 petals. So one of the things we could do is we could just sort of manipulate with our window to see what would happen to make it work. Right, so we can play with it and we're like, okay, well, I don't think it needs to be 2 pi. Maybe it needs to be just pi, right? So I tried to just go from 0 to pi. Like, okay, we'll try to go from 0 to pi and we'll see what happens. And we graph it and we get the whole region again. So that wasn't good. It meant that when we did 2 pi, it actually went around probably twice, right? Because I saw the whole graph within a unit, one rotation of it. So how do we find what the values are? And not only that, but it doesn't start out very nice either. So when I go from 0 to 2 pi, right, like as it started its graph of this thing, it doesn't start out by like making one loop, finishing it, and then making another loop. So it's not super helpful that it keeps doing these loops, but it doesn't, while it starts and stops at the same place in terms of my loops, it doesn't start and stop at a full looping value, right? So it doesn't do, in other words, just this outer loop over here and stop. Right, it actually started halfway through one of the loops. Let me see if I can get my graph to do it again so that I can draw where it started with. So it actually started, right here to begin with. So my first thing that it did was to look like this, right? And then it continued on from there. Well, that means starting at 0 is probably not where I really want to start. Okay, so we can manipulate, we can play with this. There's nothing wrong with doing trial and error, except that it might take a while, right? And that might not be the most effective use of our time. So let's talk about how we could do it in a more concrete way instead of doing trial and error if we wanted to kind of maybe get to the point quicker. And trial and error is not a good choice, or maybe it's just not proving to be a good choice for the particular problem we're working on. So what we really want to notice is that when we're hitting these, the origin, we're hitting an R value of 0, right? The radius, the distance from the origin when I'm at the origin is 0. So what I really want is I want my cosine of 3 theta, my R equation, to equal 0. And I'd like to find places where it equals 0 consecutively. And so like the first place it equals 0, and then maybe the second place is equal to 0. And we can do this with what we know about unit circle and cosine. So the cosine on our unit circle, right, I'll just sketch another graph down here. On the unit circle, cosine units are x values, and cosine is actually equal to 0 at pi halves and at 3 pi halves, right? So what I actually need is I need for my cosine of 3 theta, that is my 3 theta, now the angle measure, to equal things like pi halves and 3 pi halves, and it could keep going, right? We could do 5 pi halves and 7 pi halves. But I only need the first two, so these two should be sufficient. And if I multiply by 1/3 or divide by 3 correspondingly, right, like this, I'll be able to find out what theta needs to be. So theta is actually going to go from pi over 6 to 3 pi over 6, or another way of writing 3 pi over 6 would be pi over 2. So I need my rotation to actually go from pi over 6 to pi over 2. And if I take my window and I put those in, pi over 6 for theta min and pi over 2 for theta max, I get an exact rotation. And interestingly enough, the rotation I get is this one over here, the only one I didn't highlight in earlier, oddly. So that's going to answer my question. Like that's the region that I need if I use those as my alpha and beta. So when I'm finding my area now, right, my area is 1/2, and it's the integral from pi over 6 to pi over 2 of the cosine of 3 theta, and then it's squared, right? The formula had squared as a part of the radius. It's the radius squared, d theta. All right, so we can look at our trig table. We don't want to integrate cosine squared as it is. We want to use a power reducing formula to do that. So you can either Google power reducing formulas, or you can actually take one of your double angle formulas and manipulate it a little bit to find out. But the trig identity that we're going to use is the following. All right, so cosine squared of, we'll just use u, is equal to 1 plus cosine of 2u over 2. So the over 2 part's going to give us another 1/2. So instead of having 1/2 out here in front now, I'm going to have a 1/4. I still have my pi over 6 to pi over 2. But instead of cosine of 3 theta squared, I'm now going to have 1 plus the cosine of double that angle, which would be 6 theta, d theta. All right, so I'm going to find the antiderivative of that. So the antiderivative of 1 is theta, and the antiderivative of cosine is sine, right? But I have sine of 6 theta that will then be divided by 6. There's a u substitution going on in there. So you can write it like this, or if you prefer, you could also write it with the 1/6 in front of the sine theta, sine 6 theta, like this. So your preference on that. We're evaluating this at pi over 2 and pi over 6. All right, so we have some evaluation pieces to do. I think I might need to shift my pictures around a little bit to try to get some more space. That will work. So we're going to shift that up. So I have 1/4 still in front. This is pi over 2 plus 1/6. And it's sine now of 3 pi. And then I have minus pi over 6 plus 1/6 sine of pi. All right, so lovely enough, the sine of 3 pi is actually equal to 0, and the sine of pi is actually equal to 0. So the only pieces I have are the pi pieces at the beginning. So I still have my 1/4, of course, at the front. And then I have pi halves minus pi over 6. And pi halves minus pi over 6 is pi thirds. So this ends up being pi over 12. All right, so that one was one of the loops of right, a 3-looped graph. Again, the names of all of these escape me at the moment, but they're all listed as we talked about last time. in the textbook for this section. All right, so let's try another one. Same directions, but we're going to have the question posed a little bit differently. This one is actually asking for the large loop. When we draw it, you'll see what it's meaning of r equals 1 plus 2 sine of theta. I'm sorry, sine of 2 theta. 2 sine 2 theta. Okay, so we can do the same thing if you wish. We're going to start with the calculator. Sorry about that. We'll put this into y equals. So I have 1 plus 2 sine of 2 theta. And as we take a look at that, my window, of course, I am wanting to make sure that I see probably to start with 0 to 2 pi, see what happens. It might repeat over itself. It might not start and stop in a good spot, but it's a good starting point maybe. My theta step can be 0.1, just like it has been. This needs to have a little bit bigger x min and x max and y min and y max because I can get up to 3 at least on the sine theta, right? Because I have 1 and negative 1 for sine, and then I'm multiplying that by 2 and adding 1 to it. So I'm just going to go negative 5 to 5 and see if that will be reasonable enough. I think it'll be okay. And I think it's all right. We have a very interesting picture going on. So this time around, your picture looks something like this. I have these very large, like balloon-looking shapes right here and right here. And then I have these very small ones on this, in quadrants 2 and 4. So it looks something like this. So what it's wanting me to find is the area of one of the larger loops. And maybe it'll be this top one, or maybe it'll be the other one that I haven't shaded. Either way, it doesn't make any difference. They're symmetric. So again, we can play with the y min, y max, the theta min and theta max to try and make it work. But once again, we want our radius to make sure that it's hitting at the x-axis, or at the origin rather. And it actually drew that first loop first. It started and stopped. So it seems like a good place to start with just setting it up like we did last time, where we have the 1 plus 2 sine 2 theta equal to 0, right? So we'll start with that equaling to 0, and we'll see what happens. So I'm going to subtract my 1 and divide by my 2, so my sine of 2 theta is going to equal negative 1/2. On a sine curve, a sine graph is equal to a negative value if we're in quadrants 3 and 4. Right? And we can get there either by going backwards or by going forwards. If you take a look at this one, when we go forward, I don't think it started at quite the right place. So let's just take a look together. All right, so let's actually just mark this and see if we can get our marking to work out the way we wish. So in order for us to be looking at the sine value equaling a negative 1/2, it means we would need to be somewhere around here. So here, right, depending on what we want the sine value to be. Because it's the sine value to equal 1/2, that's the y value, we actually want it to be this one right here. That way I marked second. And that actually is at negative pi sixths. So I want my angle measure, which is 2 theta, to start at negative pi sixth. And I need it to go all the way to the other sine value that's negative 1/2, which should be over here. So if this angle is pi sixth, then going all the way here would be another pi. So this is pi and then pi sixth. So that would be 7 pi over 6. And then, just like we did on the last one, we need to get theta by itself, so we'll multiply by 1/2. So my theta value actually needs to go from negative pi over 12 to 7 pi over 12. And you can check that by using those in your calculator to see that that forms your entire first loop, that larger loop that we were looking for. So my area is equal to 1/2 the integral from negative pi twelfths to 7 pi twelfths, Our angle that we're integrating is 1 plus 2 sine of theta, and all of that should be squared d theta. Now, that's not as friendly as the last one because there's addition inside there with the squaring, which means we have to FOIL it out, right? We have to do 1 plus 2 sine 2 theta times 1 plus 2 sine 2 theta. So when I FOIL that out, I end up with a 1/2 integral of negative pi over 12 to 7 pi over 12. I'm going to copy that so I can use it again. And then as I multiply this out, I have 1 plus. I'll have 4 sine of 2 theta when I multiply my inner, my outer terms together and then add them. My inner terms and add them to my outer terms. And then I have 4 sine squared theta, d theta. Now, I again have that power for sine squared, right? Like the sine is being squared. And so once again, I have power reducing formulas that I have to use. And I'll write that power reducing formula at the top. Sine squared of u is equal to 1 minus the cosine of 2u over 2. So it's very similar to the cosine squared one. It's just in a subtraction sign between them instead of an addition sign if you go back to compare those. So my antiderivative changes to 1/2. Oops, I had said that I copied that, and I did. There's 1/2 integral from negative pi halves to 7 pi halves. And I would need to change this up. So I have 1 plus 4 sine of 2 theta. That's the same. And then I have, instead of 4 times it, I'll have 2 times 1 minus cosine. And I double my angle, so it's now 4 theta, d theta. I left off my brackets. Let's put that in like that. Okay, next we're going to do a little bit of cleaning up and consolidating inside that set of parentheses. So I won't worry too much about explaining those details. I know you get the algebra point of all of that. So we'll combine the like pieces together, multiply out and so forth, and I'll end up with 3 plus 4 sine of 2 theta minus 2 cosine of 4 theta d theta. And we'll take our antiderivative. So I'm running out of space a little bit. Let me actually, I think I might be able to shrink or move up a little bit of this, and that will work. Let's give that a try anyway. There we go. All right, so this will equal, I've got 3 theta. Well, I've got the 1/2 in front first. 3 theta. And then it's minus 2 cosine of 2 theta. Right, so the reason it went from a 4 to a 2 is because I have that double angle that's creating a u substitution, so I have to divide by a 2. And on the next one, the same kind of thing. I have that, not a double angle, but the 4 theta angle, so it's a u substitution. We'll divide by 4, so that makes this a negative 1/2, and then sine of 4 theta. And we're evaluating that at 7 pi over 2 and 12, and negative pi over 12. So we'll evaluate that. We'll plug those in. So I have 1/2. I have 7 pi over 12. Well, 7 pi over 12 times 3, so 7 pi over 4 if I multiply it. Minus 2 cosine of 7 pi, and it's a double angle, so it's 7 pi over 12 times 2, so it's 7 pi over 6, minus 1/2 sine of 7 pi, and on this one it's a 4 power angle, so 12 becomes a 3, 7 pi over 3. And then we have minus, and I have a negative pi over 4, again because I'm using the negative pi over 12 times the 3, minus 2 cosine of negative pi over 6. Again, I'm reducing the angles as I go, and then minus 1/2 sine of negative pi over 3. All right, so unit circle situation and simplifying as we go. I have a 1/2 at the front. I now have 2 pi plus square root of 3 minus square root of 3 over 4 plus square root of 3 and minus square root of 3 over 4. So a lot of uncombinable things in there, but a couple things that we can combine as well. So we've still got our 1/2 on the outside. As we're simplifying, I'll do that one more step. There's a 2 pi inside. And if I combine all the radical pieces that I can and so forth together, I have 3 square root of 3 over 2. And if I distribute the 1/2 through, this would give me pi plus 3 square root 3 over 4. So as not pretty maybe as that looks, that would actually give me what I'm looking for, right? The area of the larger loop. Okay, so when I originally created my notes, I fully intended and wanted to show you the derivation of the next formula as well, but given how long the first formula took, I decided that I would forego that this time. This is Theorem 1014, and it's a theorem about arc length. And of course, it's in polar. That's what we're working on in this section, and it says the following. Let f be a function whose derivative is continuous on alpha to beta. And it's the open interval alpha to beta is all that we need. The length of the graph, right? If we were to measure the length of the graph, of r equals f of theta from theta equals alpha to theta equals beta is, and again, when we look at area, we look at a capital S. When we surface area, when we look at arc length, we look at the lowercase s. We're using that same notation here. It's the integral from alpha to beta, and this will look somewhat familiar from the things we've done before. It's f prime of theta squared, and then it's plus f of theta squared d theta. Or an alternate version of this would be to do the integral from alpha to beta of the square root. Let me shift this over just so they line up. Of dr d theta, right, the derivative of r squared, plus r squared itself. So that's another version of the exact same formula. All right, we have one example left to show you how this works and how lovely it is. And then we'll be done with this section, so bear with me, we're getting close. All right, so I'm not going to have space to put it all here, but I'll actually start it here just so we can start it, and we'll copy and paste to the next slide when we need to. So this is the example we're looking at. Find the arc length of the given curve. And the form we're going to do is one that we've seen similar forms to this show up on others for different purposes. R equals 2 plus 3 sine of 3 theta. And eventually, if you take a look back at that formula again, we need dr d theta, so I'll find it right now. So this would be, the 2 would be 0, of course. 3 sine 3 theta would become cosine of 3 theta. But the 3 here would actually get multiplied by the 3 down here, right? So if you wish, we could do that all at once, and instead of putting a 3 at the beginning, we could just multiply the 3 that's on the outside by the 3 that's part of the chain rule. It gives me a 9. So the derivative dr d theta is 9 cosine 3 theta. And we'll set up the antiderivative on this screen, and then I'll copy it to the next screen. So this is s equals, and it's the integral. And we can look again at our limits of integration in order to see the arc length of the given curve and so forth. It actually goes from 0 to 2 pi on this one, so we'll kind of shortcut that for the sake of time. And then we want the square root, and it's of r d theta, so that's 9 cosine of 3 theta squared, plus, and then I want r squared, so 2 plus 3 sine of 3 theta squared, d theta. Okay, it's on the next screen now. Very good. All right, so we're going to just, multiply some things out, clean some things up, just like we did on the last problem, but for, of course, the purpose now of finding arc length. So from 0 to 2 pi, we have the square root. As I'm simplifying and multiplying these out, I've got the first one is 81 cosine squared of 3 theta. My next one should be foiling, right? So I'm going to end up with 4 plus, and then I'll double those, multiply the two together and double them. That would give me 12 sine of 3 theta, and then plus 9 sine squared of 3 theta, d theta. So it's not super friendly that I have both sine squareds and cosine squareds here, but they don't have the same coefficient. So I'm just going to combine them by changing one using the Pythagorean identity into the other one. So we're going to go with the 81 changing. It doesn't really matter if that's just the one I'm picking. So this would be 81 times 1 minus sine squared of 3 theta plus 4. Let's see, what else do we have? Plus 12 sine of 3 theta and 9 sine squared of 3 theta. D theta, of course. So when I distribute that 81 through right here, and I combine the like terms, I'll be able to do some condensing. All right, so we have 0 to 2 pi, the square root. We have 85 plus 12 sine of 3 theta, and then we have minus 72 sine squared of 3 theta, d theta. And while we could certainly change this, using a power reducing formula and so forth, the fact is we have a square root of it, and that doesn't help. And not only that, but I also can't factor this to somehow eliminate the square root and the squares. It will not work for us to consolidate this. Sometimes it does, and sometimes you can factor it into the perfect square trinomial. We had an example of that the other day, and that's beautiful. But when we get to this point and we're not able to do that anymore, we will use a calculator. So we need our calculator now. And I don't know, we haven't done this in this class, but maybe you've done it, I hope so, in a different class. Use your calculator to find such an antiderivative. So we're going to use the Math 9 feature. Math 9 allows you to take the equations that you're working with and to find the integral. And so I can show you what mine looks like. It looks like FN INT, function integration. And some of yours actually, when you hit Math 9, will actually pull up this kind of a box, and it has these I'll draw them they're little dotted right here, and it says like this, and it has a D, and it does another box right here. So these are the two different versions of things that can come up. So if you've got a version of your calculator that looks like mine, the operating system in it, you need to tell it that you want it to take the equation that's in R1, that you want the theta value to, or the variable to be theta, that you want it to start at 0, and that you want it to go to 2 pi. If you have this other version, the newer version, which is probably what most of you have at this point, you're going to put a 0 at the lower integral limit, the 2 pi at the top one, R1 goes in the middle, and theta. So I'm going to put that right now into my calculator. You might be asking, well, how do I get R1? We can, oh, and then I went and deleted it. Oh, I haven't put it in my calculator yet anyway. So I have the square root of 85 plus 12 sine of 3 theta, and then minus 72, and then sine of 3 theta, and I'm going to square the sine. And then I'm going to hit, like I said, I'm going to hit math 9. I'm going to do hit my vars, y vars. I'm in polar, and then I do R1, comma theta, comma 0, comma 2 pi. Or you put those in the corresponding places that we just talked about. And when we press enter, it will do its calculation. It'll spin, the spinning wheel of death for a little while. And it eventually will pop out with the final answer. It's using numerical integration to do this, and so it takes it a while. And it will tell you that the answer is, with 2 decimals of accuracy anyway, it's 41.54. And if you're using a different, or if it tells you to use a different level of accuracy, of course, go with however many decimals that it asks you to use. So that's our best approximation. I really should put approximation in here instead of exact value. All right, so that's it for this section. The good news is that although the lesson was very long, the homework isn't. So this is page 735, and we have problem numbers 8, 9, 14, 17, 53, 56, and 58.